Welcome to Topic 3, Design for Six Sigma. Now, Design for Six Sigma, or DFSS, ensures that a new product or service meets customer requirements and a process is at Six Sigma level using tools such as QFD, or Quality Function Deployment, and an FMEA, which is a Failure Mode Effect Analysis. Now, Design for Six Sigma is used to introduce a new product or service or a category of product or services. It's used to improve a product or service or to add to an existing product or service line. Now, there are two major processes for Design for Six Sigma. The first one is IDOV and the second one is DMADV. Now, IDOV, or IDOV, stands for Identify, Design, Optimize, and Verify. With Identify, we identify customer needs to design the product or service. In the design phase, we design alternate concepts by identifying functional requirements. We select the best fit and predict a Sigma capability. In Optimize, we optimize it by calculating tolerances using a statistical approach. And then finally, in Verify, we verify the design by testing and validating and then checking for conformance to a Six Sigma standards. One of the more popular Design for Six Sigma methodologies is DMADV. It is really similar to DMAIC, but with a couple of differences in the last two phases. DMADV. It begins with define, then measure, then analyze, then design, and then finally verify. In the define phase of DMADV, we define the customer requirements and goals for the process, product, or service. In the measure phase, we measure and match performance to our customer requirements. In the analyze phase, we analyze and assess the design for the process, product, or service. In the design phase, we design and implement the new process, and then finally, we verify the results and maintain the performance moving forward. So the comparison between DMAIC and DMADV is really similar. But with DMADV, we're always going to be starting a new process. This is where a process or a standard operating procedure does not exist for that particular product or service. We're literally creating it for the ground up. In DMADV, we're not creating new processes. We're improving processes that have already been created. So a good example would be is we would start this new process by using a DMADV or an IDOV approach. Once that process has been functioning and then we realize that it could be broken, then we would come back and apply the DMAIC methodology to fix that process. Now, the IDOV and DMADV approaches differ in a few ways. Now, with IDOV, it can be used to design a new product or service, or when a new process is designed. The design step follows the identification of customer requirements. With DMADV, now it can be used to design either a new or an existing product or service. It's used with an existing process when it's being redesigned. And the design stage comes only after defining requirements and analyzing the existing product, service, or process. Now, Quality Function Deployment, or QFD, is a systematic process to understand customer needs and to convert them to a set of design and manufacturing requirements. QFD, or Quality Function Deployment, helps an organization to prioritize customer needs, such as which customer needs are the most important. It also helps to set targets to meet those needs. So what are the strengths, the weaknesses of the system, and where should all of our efforts be focused? In QFD, it is necessary to ask customers relevant questions and to tabulate that data so that we can identify a set of parameters that are critical to the product design. So one of the tools that we use is called a failure mode and effect analysis. Now, a failure mode and effect analysis, or FMEA, is a preemptive tool that helps us to identify any potential risks or pitfalls at all levels of the business system. And an FMEA helps to identify failure modes of a product or service and then prioritize them. It also helps us with possible effects of the failure on the customer and also critical areas within our system. Now, a drawback to an FMEA is that although it helps to focus attention on critical areas of the system, it does not give a solution to those identified problems. Now, there are two types of an FMEA that we'll be discussing in your Greenbelt course. The first one is called a PFMEA, and the second one being a DFMEA. Now, a PFMEA stands for Process Failure Mode Effect Analysis, while the DFMEA stands for Design Failure Mode Effect Analysis. With a PFMEA, they are used on new or an existing process to uncover potential failures. They're done in the quality planning phase to act as an aid during production. And it involves fabrication, assembly, transactions, or services. Now, with a DFMEA, they are used in the design of a new product to uncover any potential failures. They're aimed at identifying failure mode defects and reducing them. And it's done before a product is sent into manufacturing. All significant design deficiencies would be resolved by the end of a DFMEA process. So let's dig deeper into an FMEA. To do that, we have to understand something called a risk priority number, or an RPN. A risk priority number is a measure used to quantify or assess the risk associated with a design or process. It begins by assessing the risk, which will help us identify critical failure modes. The higher the risk priority number, the higher the priority the product or the process receives. And an RPN is calculated using severity, occurrence, and detection, which are then given a value of a scale of 1 to 10. So for instance, your RPN, or your risk priority number, is your severity multiplied by your occurrences multiplied by your detection. So what is the process to discover a risk priority number? Well, first off, we have to understand what process are we looking at. What's the process step? So that's the first thing. What step? Every process has a potential to fail. If that process fails, we are not going to be able to meet our customer requirements. So we have to understand what step we're looking at. The second thing that we want to identify is what could go wrong with that step. What are any potential failure modes? So what could go wrong? Now, there's no way that we're going to be able to completely identify 100% of the failure modes. But it's our job as the Six Sigma project team to really start understanding what could go wrong with our particular process step. Now, once we find out what could go wrong, then we have to see how severe those things could be. And we rate that 1 through 10, with 1 being it's not severe at all. In fact, it would probably have no effect on the customer and they wouldn't even realize that it happened. To 10 being it's the end of the world. Like literally, if this thing fails, it is absolutely severe, to the point where even there could be serious injury or people could lose their lives. Once we gauge how severe of a failure mode it is, the next thing we have to do is we have to identify how it could even happen, how often it could happen. So how often? And we would still rank that 1 through 10. With 1 being it would hardly or possibly never even happen, to 10 being it could happen all the time. Once we understand severity and once we understand occurrence, the next thing we have to find is detection. So how easy is it for us to detect the failure? And we'll do that between 1 and 10. With 1 being, it's not easy at all for us to detect the failure. And 10, oh, I'm sorry. The next thing that we have to do is we have to decide how easy it is for us to detect the failure. With 1 being, it's incredibly easy for us to detect the failure. In fact, we would notice it every single time. To 10 being, it's impossible for us to detect the failure. We would never see it. So our RPN number is calculated using that scale. Now, going back to mathematics in school, we understand that 1 times 1 times 1 is still equal to 1. So this, even though has low severity, has low occurrences, which means it's not severe, it never happens, and it's easy to detect, this would have almost minimal or no effect on our customer. So then it would be 10 times 10 times 10, which is 1,000, which would be the absolute worst case scenario. So our RPN is going to range from 1 to 1,000. Now remember, the higher the RPN, the higher the priority that particular failure mode is for our plan. So the FMEA table helps in planning improvement initiatives by underlying the why and the how that the failure modes occur, and they plan for their prevention. So in this particular table, it begins by understanding the process step and the key process inputs. So what is the key process input and what is the process step? Then we have to list what the potential failure mode is. So in what ways does that key input go wrong? Then we look at the potential failure effect, and then we look at severity, we look at potential causes of that severity, the occurrence, then the current controls that are in place, and then for detection. And that's how we get the RPN number. So let's look at some scales in terms of how we can start gauging what RPN looks like. And we'll begin with severity. Now, severity is just the measure of how critical the failure mode is to the customer or to the process. A high severity rating indicates a mode is critical to the operational safety, and the rating can never be changed. So it begins with the most severe. We kind of talked about this before. It's hazardous without warning. There's a very high severity ranking when a potential failure mode affects safe system operations without warning, and that would be ranked as a 10. Then you go to hazardous with a warning, which would be a 9. And then I would typically do 1 through 8 based upon none would be typically a 1, very minor would be a 2, and we work our way up that way. Now, occurrence is the probability that a specific cause will result in a particular failure mode. The higher the occurrence of the failure, the higher the rating. And then we looked at detection, which detection is the probability that a particular failure will be found. Now, if detection is impossible, the failure is given a rating of 10. At the start of a Six Sigma project, the failure mode is given a relatively high detection rating. And the reasons why we would do that is because that's the reason why we're doing our Six Sigma project to begin with, is because this continues to fail and we have no detection capability for it. So here is a process of withdrawing cash from an ATM. The bank wants to recognize and prioritize the risks involved. So the first thing that we have to do is we have to identify the product characteristic, which in this case is cash withdrawal from an ATM. So what are the potential failure modes that could happen in that process? Well, the customer account is debited, but the cash was not paid through the ATM. So the customer had the withdrawal marked on their statement, but they never received the cash. So what could possibly cause this failure? Well, the effect of this failure would be an extremely unhappy customer. I mean, I would be upset if I went to an ATM machine and I put in my PIN and it said that I was going to receive my money, but the money never came out. So I'm going to mark that as a 9, that is highly severe. That is severe. That is an incredible amount of pain for the customer to go through. So what are the potential causes of this? Well, there's 2. The first one is the non-availability of cash within the ATM. So the ATM is just empty. There's no more cash left in it. The second one is there's a network issue or a communication issue between the ATM machine itself and the bank's network. So if it's a non-availability of cash, that's at a higher occurrence. That could occur more often. So we're going to put that as a 7. But the network issue we're going to put as a 5 because that doesn't occur as often. So what are the current design controls that are in place to stop that from happening? Well, with the non-availability of cash, we can set a minimum limit warning. So when the total cash reserves in the ATM gets to a certain point, it would then send an alert out to the bank to get the ATM refilled. But currently, there isn't a known design control within the network issue. So the detection of the problem is fairly easy with the cash in the ATM, so we're going to give that a 2. But since there isn't a current design control in place for the network issue, we can't detect that, so we're going to give it a 9. So when we multiply that through, the RPN is 112 in regard to the cash in the ATM, and 405 in regard to the network issue. So which one is more important? Well, remember, the higher the RPN, the higher the risk. So therefore, we need to look at the network issue first. So what are our recommended action steps? Well, with the cash, we're going to increase the set limit so that it's known more regularly, that we'll be able to get those limits sooner because we're going to raise the set limit to where instead of, let's say, there being $1,000 left in the ATM, now we're going to say when there's $10,000 left in the ATM, it's going to let us know. And well, who's responsible for that? Well, it's management that's responsible. Well, then what about the network issue? Well, we're going to increase our network limit. Maybe that's the throughput. Maybe that's the amount of data that can be transported between the ATM and the bank's network. Well, who's going to be responsible for that? Well, technical and management, or IT and management. So what are our actions taken? Well, on the cash side of it, we just increase the minimum. And then we also increase the limit in terms of load balancing for the data. So what's the severity if it fails again? What's the severity if a customer tries to withdraw cash and they don't get their money? It's still a 9. So severity didn't change. Now occurrences kind of moved a little bit. Now it could increase our occurrences with non-cash availability. But if you notice, it completely decreased almost the network issue. It went from a 9 to a 2. Detectability went down for both of them. So now detectability in terms of the non-availability of cash is almost negligible. It's almost non-existent, right? Which means we can detect it almost 100% of the time because it's a 1. And our detectability in terms of the FMEA also went down from 9 to 3. And then finally, our new RPN is calculated, and it's 32 for the ATM cash withdrawal and 54 for the network issue. And that concludes learning all about an FMEA.